Welcome student. Today our topic is pumping lemma for regular language and context-free language. Okay. So initially we will discuss the first part, that is the pumping lemma for regular language. So now what is pumping lemma? First we need to understand that. Pumping lemma is basically a lemma or a theorem through which we will able to determine whether a language is regular or not. If it is a context free, so whether it is context free or not. Okay. Then this is the theorem which we first need to understand. Okay. And then we will exercise some examples. Okay. And through those examples, I think our understanding will become much easier and much be in point, to the point, or perfect. Now, what should we start from the point? From the point where should we start our discussion to understand this pumping lemma? Is the lemma itself. By you can see that if n is a regular language, then for any positive integer m, we can choose any sentences w belongs to L. W belongs to L such that mod of w means what? It is the length. That is the length of the sentence. Suppose it is ABC, so length is 3. Suppose it is ABCDE, so length is 5. If I consider the whole alphabet, so length is 26. If I consider A square and B square, the length is 4. If I consider A square B, the length is 3, because 2 number of A and 1 number of B. So the mod of w means the length of the sentence. Mod of w greater than equals to m. Okay. Now, if w is divided into 3 parts, x, y, and z, such that mod of xy is less than equal to m, and mod of y is greater than equal to 1. Now, one thing we should understand by this representation is that the length of x may be, sometime it may become 0, but the length of y cannot be 0. Okay, it always greater than equals to 1. The minimum length of y is always 1. Now, then for all I equal to 0, 1, 2, 3, all of these, the pumped string which is w suffix I, wi is that is equal to x, y to the power I, z, and that belongs to L. Okay. So this is basically what you can say that the pumping lemma. Okay. Now we will understand the entire thing to some examples. Our first example is this one. See here. Here the language is, see my mouse pointer here, and you can understand it is a to the power n and b to the power n, where n is greater than equals to 1. Now, through pumping lemma, we need to check whether this is regular or not. This language is regular or not. So initially, we are considering that this is a regular language. Okay. Now, now as in the previous slide, see what we have till here, that we will consider positive integer m, okay, to determine the length. Now here also I am considering for any positive integer m, we choose the sentence a to the power m, b to the power m. Why? Because your language is a to the power n, b to the power n. So now for m, as we always consider it using the m, as we always consider it using the m, so it is a to the power m, b to the power m, and that definitely belongs to L. Now, mod w means the length of the string, okay, that the length of the sentence that we are considering a to the power m, b to the power m. So it is mod of w equal to mod of a to the power m, b to the power m, and that is equal to 2m, okay, because m number of a and m number of b, and which is the 2m which is greater than equal to m, definitely. Now the sentence w is divided into 3 parts, okay, x, y, and z. W divided into 3 parts, x, y, and z. Now I am writing it what? W equal to x, y, z equal to a to the power p, a to the power q, and b to the power m. Okay. So that means this a to the power m, this a to the power m, okay, it is divided into two parts. So you can see that I'm telling about this a to the power m, which is divided into two parts, that is a to the power p and a to the power q. And I have left the b to the power m as it is. Now, so our this x and y, when you calculate the mod of xy means the length of x and y part. So mod of xy equal to this a to the power p, a to the power q. There is basically p plus q, okay, and that is equal to m. Clear? Because it came from where? It came from a to the power m. Okay, this part is basically came from a to the power m, because I have written a to the power m, that is equal to a to the power p and a to the power q. So definitely it is p plus q equal to m. Okay. Now also the mod of y equal to q, because mod of y is basically a to the power p. So as y equal to a to the power q, sorry, the y equal to a to the power q. So mod of y equal to mod of a to the power q, and that is basically the length, that is the q, so greater than equal to 1. As per the algo, we know that the length of y, mod of y, the length of y, which is basically mod y, that is definitely greater than equal to 1. Okay. Now for I equal to 0, as we have seen in the algorithm part, that is the I equal to 0, for I equal to 0, 1, 2, 3, this is basically our palm string. Which one? This one is basically our palm string. So according to the value of I, we will put the values over here. Now, so in our example, if we put the value of I as a 0, so we get it is W0 equal to x, y to the power 0, and then z. Okay, and it is a to the power p, a to the power q whole to the power 0, because it is the y. Okay, and b to the power m. So as it is 0, so this part becomes vanishes, and we have a to the power p, b to the power m, which is not belongs to L. Why it is not belongs to L? Because p not equal to m. Why p not equal to m? Because p plus q is equal to m, and the q part is not 0, because q is the y. Okay, and that greater than equals to 1. So that means p not equal to m. So it means this p plus m not equal to your 2m. Okay, because p not equal to m. So for I equal to 0, our pumping lemma is violated, and we have reached at a contradiction, and our initial assumption was wrong. So L is not regular. Okay, so this is the way by which we are solving this problem. This is, see, in pumping lemma we will solve the problem. For different category of problem, we have to take different approach. For this kind of problem, this is the approach. Okay. Now again, for a similar kind of problem, let's see another example. See, this part is another example. This is another example of the same category, belongs to same category. Okay, where it tells that L equal to WWT. T means transpose, the opposite of T, and W is consist of A and B. Okay, A is B star. So it is basically a palindrome, nothing but a palindrome. Okay, there's A, B, B, A. So now I am considering for a similar process, is very similar. For any positive integer m, we choose a sentence a to the power n, b to the power m. This is the W. So definitely WT is the opposite of this. So it becomes b to the power m, a to the power m. Okay. So 4 number of m number of A, m number of B, m number of B, and again m number of A. So mod of W is equal to a to the power n, b to the power m, b to the power m, and a to the power m. So it is 4 number of m, 4m, which is definitely greater than equals to m. Clear? Now the sentence W is divided into 3 parts. W equal to x, y, and z. W equals to X, Y, and Z. Okay. Now I'm dividing the first part, that is the a to the power m, what I have done in the previous example, the a to the power m into two parts. So it is a to the power p and a to the power q. And rest of the part, b to the power m, b to the power m, b to the power m as it is. Okay. So same thing, mod of xy equal to mod of a to the power p, a to the power q. So it is p plus q equal to m, and other things remain same. Now again, for I is equal to 0, for I is equal to 0, the pumped string W0 equals to x, y to the power 0, z. This is your x, this is your y, and definitely the power is 0, and this is the rest of the thing, that is the z. Okay. Now, as it is 0, the power, so this term becomes vanishes, it becomes p plus this m, and m. And again, it is same, that it is not belongs to L. Why? Because p plus q is m, and q is definitely greater than equal to 1. So p cannot be m. As q is greater than equal to 1, so p cannot be m. That means p plus 3m, p plus 3m not belongs to or not equal to 4m. Okay. So for I equal to 0, the pumping lemma is violated, and we have reached the contradiction. So our initial assumption was wrong, and L is not regular. Clear? Done? So what is the approach actually we are following in these two examples? Basically, if I ask you what is the trick to solve this previous two type, very simple. That is, divide the first part into two pieces, x and y, and consider the remaining part as z. So we have got your x, y, and z. Okay, done. Then I is equal to 0 and this one. Clear? Now the another type of problem. This is the same one, that is example 3, which is belongs to the type example 1 and 2. So you can solve it by yourself. Okay. If any problem will occur, definitely I will come to help you. Now another category of the problem, that is a square, sometimes square or cube. If this triangle problem, a to the power n square. So now same approach. First, initially we consider it as a regular. Okay. Now for any positive integer m, it is a to the power m square, which belongs to L. So mod of w is equal to mod of this, which is equal to m square, which is greater than equal to m. No problem. Now again we divide it into three parts, x, y, and z. Mod of x, y is equal to p plus q and whatever. Now your definitely a question should arise in your mind. Sir, in the what is the question? Sir, in the previous examples, we have divided a to the power m into x and y. But here, what should we do? Because there is only a single term, that is a to the power m square. So here the approach is slightly different. What is that? Now for I is equal to 2, not 0, I is equal to 2. Why 2? Because we are considering with the square. Okay, if we deal with n a to the power n cube, then we must take the value of I equal to 3. Okay. Now the palm string W2 equal to x, y square z. Yes, definitely is Wi, as if you can recall the palm string, it is Wi equal to x, y to the power I, then z. So here, as I equal to 2, so W2 equal to x, y to the power I, z. Clear? Now you can see this one, that W2 equal to x, y square and z, mod of this, definitely. So mod of x, y square, z can be divided into two parts. The first part is mod of x, y, z, and another part is mod of y. So mod of x, y, z is definitely, it is mod of y. Mod of w, as we are considering into three parts. Okay, see this, w is equal to x, y, z. So mod of x, y, z can be replaced by w. So mod of w, and mod of w is definitely m square. See this one with this line, this mod of w is definitely m square. Okay, what we have written previously. So the value of mod of w can be replaced here. Okay, and it becomes m square plus mod of y. And as per algorithm, we know that mod of y greater than equals to 1. Okay, we know this one from the algorithm. So see my mouse pointer, you can understand this clearly. So mod of y greater than equals to 1. Therefore, if we put the value of mod y in this equation, we will get it mod of w2, that is greater than equals to m square plus 1. It is not become equals to, it become greater than equals to. As I have put the value 1, which is the value of y, mod y, and that is greater than equals to. So the equation become greater than equals to. Now if I omit this 1 or remove this 1 from the right side, so this greater than equals to equation become only greater than. Okay, this greater than equals to equation become only greater than. So mod of W2 now greater than m square. Okay, so the first part of this problem is done. Now think about this line, this m square plus mod y, and we will start the second phase of this problem from this line again. Okay, so from that line, if we start the second part, see mod of W2, see this one, see my mouse pointer here and you can understand it clearly. Mod of W2 equal to m square plus mod of y. Okay, now as we know, mod of xy is less than equal to m. Definitely we have done this one before. So mod of y, definitely it is less than equal to m. Now your question should arise in your mind, sir, why it is remain same? Because we know that mod of y greater than equals to 1 always, but mod of x can be 0. So if we remove x from here, which is the 0 value, so the equation which is less than equal to remains same, because nowhere it is tell that what is the minimum value or the maximum value of x. So mod of xy less than equal to m, then after removal of x, which is can be 0, so it remain less than equal to. Okay, so mod of y also less than equal to m. Now if we put this value, the value of mod of y which is less than equal to m in this equation, then we have mod of W2 which is equal to m square plus mod y. Now it become less than equal to m square plus m. Why less than equal to? Because this relation I have applied here. The value of mod y, when I put the value of mod y, the equal to relation become less than equal to. Now in the next line, I have add one m and one. Okay, a single one here. So for this one only, because we cannot say the value of m, the value of m may be 0. Okay, so but as we have add this one, for this one, this greater than equals to equation, less than equal to equation become only less than. And you know, better know that this m square plus 2m plus 1 is basically m plus 1 whole square. Now, so if we consider this equation number 2, and if you remember the equation number 1, which we have previously, where we have written that mod of W2 is greater than m square. It is greater than m square. So if we combine this equation number 1 and this equation number 2, what we get? We get this thing, that is m plus 1 whole square greater than mod of W2 and greater than m square. It means mod of W2 is such a value which reside in between two consecutive perfect square. So if a value reside in between two consecutive perfect square, suppose 4 square and 5 square, so that means in between 16 and 25, if the value is 19, so the 19 cannot be a perfect square because it lies in between two consecutive perfect square. Okay, so our initial assumption, where we have assumed that the length, that is m square, which is a square number, is a wrong thing. Our initial assumption was wrong, so L is not a regular. Clear? So this example is basically another type, okay, to prove that whether, or to check whether a language is regular or not using pumping lemma. Okay, clear? Now my question is that instead of a to the see my mouse pointer here, okay, and you can understand this a to the power n square, instead of n square it is n cube. So what should we do? It is very easy. Here I am taking m square, so definitely it become m cube. Okay, these three parts and all these things are same, but definitely it should not be I is equal to 2, it is I equal to 3, and it is x y square z. Instead of x y square z, it become x y cube z. Okay, and then it divide into x mod of x y z and mod of y square, and the rest of the part is as same as it is. And definitely I think you have understand, in that case we need to prove it that it lies in between two consecutive perfect cube, that is m plus 1 whole cube and m cube. So by that way you can prove it. So this, what is that? The trick to solve this problem, this kind of problem, is first consider the length is a square number and then prove that it lies in between two consecutive perfect square. So job is done. If it is a cube, same thing. First consider the length is a perfect cube number and then prove that it lies in between two consecutive perfect cube. So then you can prove it is not a perfect cube. Okay. Now next, this is the problem which I am talking about now. Okay, so that problem, now you will discuss this thing, this problem, or you can solve this problem by yourself. Okay, you can solve this problem by, okay student, so this is a to the power n cube, this problem. Definitely you can solve it by yourself. Okay, now we should go to the next part. Okay, that is the next problem, and that problem is also belongs to another type of category, where you can see that we need to understand that whether a language L, okay, you can see the mouse pointer, is L a to the power p, where p is prime. Okay, now what the approach we should take? See, the same thing, that is we are here considering one m, okay, such that w is equal to a to the power t, where a to the power t belongs to L, then mod of w equal to mod of a to the power t, and which is equal to t, which is greater than equal to m, then three parts x, y, z. Now here we are taking some slightly different approach, and the approach is like that when it is we are considering that a prime, so we try to prove it is at a not prime, and if we are able to prove it that it is a not prime, so our initial assumption is wrong. Now how to prove a number not prime? If we are able to represent the number equal to, suppose, multiplication of two numbers, suppose x into y, where x and y, none of them are 1. Okay, if x into y, both of them are integer, definitely a positive integer values, and none of them equal to 1. So definitely if we are able to represent a number n equal to x into y and none of them is 1, so that means x is not a prime. Now here what we are doing, we divide the number into three parts, x, y, z, and a to the power p, a to the power q, a to the power r. These three are basically our x, y, and z. Okay. Now the same thing, that is mod of xy equal to mod of a to the power p, a to the power q less than equal to m. Okay, and mod of y, that is equal to q, that is greater than equal to 1. Okay. Now for I equal to p plus r. Now the question is why I am considering this kind of value for I. Okay. Now we'll see it later. For I equal to p plus r, w of p plus r equal to, that is the suffix, we know the palm string. Okay. Again, if you forget, I can remember you, that is w of I equal to ax y to the power I z. This was our palm string. Okay. So now if we think this one, that is it become w of p plus r, this x y to the power p plus r z. Then this is our x, this is our y, and this is our z. Okay. So now mod w of p plus r equal to the length of this thing. So length means mod of a to the power p is definitely p, mod of this thing is definitely q into p plus r, and mod of this basically r. So this is I have just rearranged it. Okay, why? Because you can see that I have taken p plus r as common and it become q plus 1 or 1 plus q, whatever you write. So that we have represented okay, by the multiplication of two numbers, and it has a common divisor p plus r. So definitely it is not a prime. So definitely we reach a contradiction and our initial assumption is wrong. So it is not a prime and the language is not a regular language. Okay. So this is the way how to prove. So here we have discussed so many problems and the way of solving different types of problems. Okay. Now in our next lecture, we will discuss that pumping lemma of context-free language. Okay. So that sometimes called Ogden's lemma. The pumping lemma for context-free language, sometimes called Ogden's lemma. Okay. So thank you for listening. Okay. And goodbye.